In the class that we have discussed last time, uh, the topic was on power oscillations, and I discussed the SMIB system, and then for a given set of parameters, what would be the property of the system response that was discussed last time. And then we had some discussion on uh, Kundur two area model in respect to the presence of the modes, electromechanical oscillations. So we had, if you refer this slide, we have mode 1 and mode 2. These are as a local mode between the generators. And then in the two area system, we also have mode 3. That is as an inter-area mode between the group of the generators uh, between the two areas, you can say. And we have the oscillating frequency for the local mode and for the inter-area mode. So you can see that it is somewhat low. And then you can also see what will be the typical value of eigenvalues, which will correspond to the interior mode, and then those which are for local modes. So you can see that they are associated with a higher imaginary term, and thus the oscillating frequency is somewhat higher with respect to the inter-area mode. Then we move on to the later. We move on to discuss how does the power oscillation will change with the operating condition. So in the first case, we had the 50 megawatt power flow, and then we observed how do the generators in one area and how do the generator in the second area they oscillate. And then if we change the operating condition, then you find that all the generators oscillations they are in the same phase. So thus the characteristic or the system behavior for in terms of generator dynamics for power oscillations, it will all depend upon what is the operating condition, and thus in some way also related to the control action being applied here. So in general, we can say that it is very difficult to uh, say that what could be the generator behavior for a given operating point. So in that sense, we have to analyze the generator behavior for every possible conditions of operating point actually. And then we have to design our controller and say that this controller will be most optimal for the operating condition. So this was the discussion we had last time, and we move to the next one. So I hope I'm audible, I'm clear, right?
Yes, sir.
So I have another example here, and then this is a more, you can say, a larger system. So because the previous example was on a simple two area system, but this is the example for 16 generators and 68 bus in the network, and sometimes we call it as New England, New York model or the network system. So this part or this area is actually New England system, and this part is New York system. And then we also have some more uh, equivalent generator representation. So these are actually large generators represented by one generator actually here. And you can see that there are altogether, you can say, because it starts from G1 here, right? And there are altogether 16 generators here in the complete network. And then we have 68 number of buses. So we're counting from here we have 6, 7, and then this is bus 2. So it will altogether 68 number of buses in the network. So this is much more complex or interconnected network that we can consider for the study related to power oscillations. And you can see that one large generator, how they are interconnected to another system, another network here, and in New York power system. So they have a power flow through the line here, right? And then the interconnection between this part of a large generator with this section of the bus here. So, and it indicates what is the amount of the power flow in the interconnection part here, in the interconnection between the two buses it shows. And then again, we have some more interconnections between the areas, New England and New York here. So in fact, the New England and New York network, they are interconnected by these three tie lines. So we have altogether three tie lines, and you can say that for a given operating point, this is the amount of the power flow and as well the direction of the power flow, which is indicated here. Now, for this example, for this large interconnected network, we have four inter-area modes here, right? Which are of a frequency less than 1 hertz, and they have very poor damping factor, which is less than 5%. So we have all, you can, for a given operating condition it is. So we have four inter-area modes of poor damping factor less than 5% and of oscillating frequency less than 1 hertz. Then there are in addition, there are 11 local modes here. So there will be some generators, they would be oscillating in a group at a local level, you can say. So there are 11 local modes here. And the oscillating frequency of these local modes will be in this range. Somewhat greater than 1 hertz to 1.6 hertz, and they have a damping factor uh, in the range of 5.6% to 16% something here. So that is the typical mode property or the power oscillation characteristics or you may come across for a given operating condition in this network, which has just 16 machine, just 16 generators and 68 buses here. Right? Anything on this one? I will not go into detail about the other properties of behavior. Maybe we'll have to discuss on in the later part of presentation actually. But just to give you a feel that if you increase the network size, then how does the power oscillations and then the system behavior, how it becomes complex. This is actually I want to make you understand with this example here. Anything on this slide? Yes, please. No, then so I think this is the slide which I had it in the earlier chapter. So now if you recall on the S plane, we have the real axis here and imaginary axis, and then the position of the eigenvalues which will correspond to the inter-area modes. They will be of somewhat lower frequency. Then the local modes will be of somewhat here, and the control modes, those eigenvalues which will correspond to the state variable associated with the control system or the control design, they are at somewhat much higher frequency here. So we have electromechanical oscillations, and then we have control modes, and this is the in general representation. How does the eigenvalues corresponding to these modes will lie on the S plane here. Okay, so I would switch over to another part here, and in fact I have few slides from the GIAN course that we conducted in the month of November 2017, and we had this course delivered by Professor Sattel from NTNU, and he was at MNIT to deliver the course during that period. So I don't have the slides, his slides merged with mine, but I will just quickly move to the slide which I want to present for this topic. I will just give you information from where you can refer some of his lectures on the YouTube that I'll have it later on. Then, in fact, just so as I said that I can start from here. So I have earlier discussed what is the small signal stability analysis, and that is somehow we say as modal analysis. So this we perform for a linearized system, with the system being represented as a state space, state derivatives here. And then we have a model transformation in the form of some other states, and we get eigenvalues, we get right eigenvector, we get left eigenvector here as a part of model analysis. Then from the complex eigenvalues, so we get the information about the oscillating frequency, and then we get the property that is the damping ratio, and this is how we define it here. And then from the eigenvector complex pair, this defines the mode shape here, the real part and the imaginary part here. All this I think we have discussed earlier. I will skip maybe if you just to recall, if from the eigenvalue property, if the eigenvalue has the real part and if it is a complex eigenvalue, then the mode definition, so it will be associated with the exponential function for a real or a non-oscillatory eigenvalue. And if it is a complex pair of eigenvalue, then it will be associated with some cosine functions oscillations here with the exponential as well. So there are two terms associated here. So this could be a decaying component or exponential increasing component, depending upon what is the sign of alpha here, the real part here. And it will be varying at some oscillations associated with the frequency. Mode type could be aperiodic, as in this case, because if you have a real eigenvalue, it will be aperiodic. But if it is a complex eigenvalue, it will be always oscillatory because it is associated with an imaginary term here. This could be now the response of a real eigenvalue could be for a first order system. So because we know that if it is only represented by 1 plus st. So if the system is represented by first order system, in that case the eigenvalue will be the real part. But if the system being as a second order or higher terms, so then it will be of as a underdamped response, and which will have a complex eigenvalue. So it will be for a second order system or higher order systems. Now, depending upon the value of alpha, the real part, if it is less than zero, you are likely to have a decaying component here in the response of any state variable with respect to time. So any state variable associated with this eigenvalue, uh, which for which the value is less than zero, it will always be a decaying value, decaying response of state variable x with respect to time. But if the real value is greater than zero, you are likely to have a increasing, exponential increasing magnitude form of response with respect to time. Similarly, if you consider a complex, then since it is associated with an oscillatory response, so thus the response of the state variable associated with this eigenvalue, which is a complex eigenvalue, will always have an oscillation. But again, depending upon the real value, depending upon the real component, it will be a damped value. It will be a decaying one. But if in case the real part of the complex eigenvalue, it is greater than zero, then it will have an exponential, as in this case, it will have an oscillatory, but the oscillatory response will be exponentially increasing actually. So that is the typical behavior that you observe for the modes. So depending upon how the eigenvalues are, either real or the complex here, right? And I think we have discussed earlier that if we want to understand the how the systems oscillate with respect to each other, then we are interested to determine the participation factor and the mode shape here. So I think I will not discuss about transfer function residues because we have not discussed earlier, but mode shape and the participation factor we have discussed, which is as a part of modal analysis. Now with this information, so if you have the example of a Nordic grid, then I just want to show you what is the position of the eigenvalues or the modes for the different state variables. So you can see that the controller mode. So that means those eigenvalues which are associated with the controller states. They are somewhere. They have much higher negative real value. However, those state variables which are associated with the, let's say, exciter side, so they are somewhere here, the location of the eigenvalues. And then we have electromechanic modes. It is said as you can say the local modes actually here. So they are somewhere here. And then we have in fact some because mainly in the Nordic grid system we have some very low so which are associated with the turbine states, because in the Nordic grid and the Norway region, I mean the network in the Norway region, in the Norwegian network, uh, it is dominated by hydropower plant basically. We have all the power generation from hydro, and we find that in their system we have very low frequency mode present, and they are said to be associated with these hydro turbines, and thus we have very low frequency or very low magnitude of modes lying somewhere here. So this is just the classification or the of the classification of the modes that we may observe in the Nordic grid. In some cases, we may not have these modes present. You may have just the local modes or inter-area modes and then analytical modes or the controller modes, but we don't have this form of the mode present in some part of the network. But in the Nordic grid, you find it here. And then in respect to the electromechanical modes, the location of the modes for if the damping factor is less than 5%, so you can see that these are the modes with the damping factor less than 5%. Then the modes with the damping factor between 5 to 10%, these are here. And then those modes with the damping factor between 10 to 15%, they are here. And then there are several modes which have a damping factor greater than 15%. So we are not bothered about these modes. We are actually much more concerned about the modes which have a damping factor or damping ratio, you can say less than 5%. So we are concerned about these modes here. Okay, so as you can see that we have these eigenmodes in the S plane, but we have not shown the other part here. So in the x-axis, we have the real part. On y-axis, we have the imaginary part here. I would skip. Yeah, this is just an example because from the eigenvectors. So, right. So if we have the complex value, then what could be the position of the phasors here? So you can say this phasor. So this is one mode, and then this phasor uh, here, and then the last one you can say somewhere. So these eigenvectors, depending upon what is the magnitude of the real part and the imaginary part, they can be plotted on the as plane, and thus they can be represented as vectors. So that corresponds to the mode shape, and then this will tell you how does the generators will be oscillating with respect to each other. So you can say that these generators they are somewhat age a position in oscillation against this generator here. So that's why how you can say that the importance of the mode shape in understanding the oscillations of the generators here, that we get it from the eigenvectors. Now, this slide tells you what it could be the typical phasor representation for the mode shape. So if we have a local mode, this local mode will adjust between the generators in the plant, or uh, it can be also between the uh, generators of nearby power plant. All right. So you may have some generators or generators in the two nearby power plants in oscillation with the rest of the system here. So this will be a local mode. There could also be an oscillation as a multi-machine mode. So it is possible that some generators, they may have much higher, or you can say a dominant oscillation with other generators in the same power plant or the nearby power plant. All right, and they all together will be against the rest of the system. So that could also be observed as a local mode here, right? So maybe one generator, two generators, they have much higher oscillation in the same group. All right, in the same group, and they will be oscillating against the rest of the system. So this could be as a multi-machine local mode. Now, in respect to the inter-area mode, yes, you can see that we have one group of the generators here. All right. and then they will be in oscillation in opposition against the another group of the generators here. So we have one group of generators on this side, another group of generators on this side, and they will be oscillating against each other, you can say, because the phase the displacement, the angular displacement between the generators, it is about, you can say, 160, 180 degree to each other. So in that sense, one group of the generators, they are in phase opposition with the another group of the generators. So this will be as a interior mode. So that could be the typical mode shape uh, for the generators, depending upon the types of the mode that may exist in the system here. Uh, Maybe I will not have this one. Yeah, maybe I can have this one. In respect to the Nordic grid, they have one mode of 0.33 hertz, which have a damping factor of about 5.4. And this is a interior mode. And if you remember, we have said that I have discussed also that this mode will adjust between the generators from the southern of Finland and again southern of Sweden or southern of Norway as well, you can say. So this mode is observed between the generators located in this region. Another mode that we have, which is factor. Again, this is also interior mode between the generators located in the Sweden and the southern of Norway. And there are some more modes. And we have local mode here. And then we have interior mode. And then some more modes. So in the Nordic grid system, we have several of the modes. And they have their own characteristics here. I mean the damping factor, and they will adjust. Uh, you can say these modes adjust across the whole network. So because if I say this modes, it adjusts in the North Norway only. This mode, it adjusts in this between the generators in the Sweden and the central part of the Norway. This mode with a much poorer damping factor. It is a local mode and it adjusts in the western of the Norway side of the generators. So we across the network in the Nordic grid, we have several modes present here. And then, as you can see, what could be the mode shape at 0.3 hertz something. So we find that I think in my presentation, small signal stability analysis, I have shown you how the generators located in the southern of Finland and the southern of Norway and the Sweden, they oscillate against each other. And that was at 0.3 hertz something. So this is the mode shape between the generators located in the Finland and the southern Norway and even southern Sweden here. So they are all together. You can see that in phase opposition, and this is a inter-area mode that we observe in the system here. And then this is all indicated what are the generators. Actually, these are the name of the generators basically. Similarly, another mode that we have 0.48 hertz. Now in this case, it is very difficult to characterize the generator behavior, because here in this, for this mode, we find that almost all the generators across the network, it is observed, because this mode is observed in some generators in the Finland, some generators in the southern Sweden, again in the eastern Denmark side, then some generators of the North Norway, and then again western and the southwest of Norway. So in fact, this mode property is being observed in almost all the generators located across the network, you can say. And it is very, but you can say that these modes, they are in phase opposition, but for this mode, these generators, they are in the phase split. So this, the behavior of the generators for this mode is much more complex here, because it does not adjust between just some group of the generators. It adjusts across almost all the generators in the network, right? So you have this mode being observed in the Denmark as well, south of Sweden, north of Norway, western of Norway, southeast of Norway, and even some generators in the Finland as well. So this mode is observed across all the generators here actually in the network. That is very complex behavior in the system. But if you refer this mode, it is observed only between on some generators only. All right, so that is very okay here. Then same way, 0.75 hertz mode, it is again a local, because these two are mode actually here, right? And then this one is also a local mode. It is also between some generators here. So in fact, now this one, this slide indicates, because we have performed some study related to 0.3 hertz mode of oscillation, and the line that connects Hasle and Halden, that is in fact, if I go back to the slide here, so this is Hasle, and then you have Halden here. It is south of, you can say, of Norway region. So the line that connects between Hasle and Halden here, this is 420 kV line. So they had the tip of the line, and they had kept the stability limit of something 2200 megawatt. And for that amount of the power flow, in fact, they have observed what will be the mode shape here. So we have some 0.3 hertz modes with a damping factor, very poor damping factor, you can say. And for this case, we have some of them at near about 0.5 hertz mode here, because this real axis indicates the amount of the power flow, right? So you can say that if we have 1000 megawatt power flow, most of the modes, they are of 0.5 hertz and with a damping ratio of 9% something. But if we increase the amount of the power flow, in this line, right, which is of 420 kV, so with the increase in the amount of the power flow, you will observe the modes. Which is of 0.3 hertz, and they will be of very poor damping factor. So what happens here? That means in this line is loading with the increase 1000, you have 1200, you have 1400, and let's say you have 1600. So for this line that connects between the two buses with the power flow up to 1600 megawatt, you will have a mode presence of 0.5 hertz, right? And with the damping near about 9%. But if we increase the power flow beyond, let's say, 1800 megawatt, and let's say you increase up to stability limit of 2200 megawatt. So if with the increase of the power flow in the line from 1800 to 2200, then in that case, this mode may get diminished. There is excitation of another set of the mode, and it is of 0.3 hertz and with a very poor damping factor. So if we recall the example from the Kundur book, we had with one case of 50 megawatt, another case of 400 megawatt. And thus, for the different operating condition in the line, the mode property and thus the system behavior, the generator behavior has changed. And this is the real example, you have it here. With this amount of the power flow in the line, you will get a mode, you will observe a mode of 0.5 hertz with the damping 9%. But with the increased amount of the power flow, you will get a mode excitation which will correspond to 0.3 hertz and with a poor damping factor here. So for it, the response amount of the power flow here, right? Anything on this slide? So this is analyzed for a given amount of power flow, right? It could be 1200, or it will be something maybe 1000 or 1100 something to 1100, 1200 something, 1300 something, and so on. So, but with a much, if we have the power flow which will correspond to stability limit, which is 2200 megawatt, then in that case, you will get a mode of 0.3 hertz and with a damping, relative damping of 3%. So that means if we have a power flow which will correspond to the stability limit, then the mode of 0.3 hertz will be very poor damping here. It is very poor, 3% only, and that is the stability limit. So if we increase the power flow beyond this, then the system response may become unstable. That is possible here. So this is what is shown as the power oscillations in the time domain actually. So this is what we had it as a steady state analysis on the mode property, and here is indicates, let's say this is in time second and this is the power flow. Let's say that this is your base case. This is your base case, right? So you have a base case. If you increase the power flow from the base case, if you decrease the power flow from the base case. So we have plus 200 from the base case, plus 400, plus 600, plus 800, plus 1000. So if we have increased amount of the power flow, you can say 1000 megawatt from the base case. You can see that with the increased amount, the oscillation, the amplitude of oscillations has increased actually comparatively. The amplitude of oscillations increases with more loading on the line here. But if you reduce the power flow, if you reduce the power flow from the base case, you reduce by minus 200, it is by minus 400, minus 600, and so. So if you have reduced the power flow by 1000 megawatt, you see the oscillation comparatively reduced. You can say because in 8 seconds, after 8 seconds, the response gets damped out actually, right? It gets damped out. But if you have increased amount of the power flow, even after 8 seconds, there is an oscillation being observed, right? So thus it is very important that how much loading you apply on the line such that the oscillations remain minimum. Okay, so this is the dynamic study on the power flow which has been analyzed on this slide and shown here, that how, if we change the amount of the power flow from the base case, how does the oscillation will change from the base case. Yeah, same way. Now here they had it from you can see that they had zero power flow, 0 megawatt delta change, 0 megawatt. So you can see that this is the black line and we don't have any, this is the one, right? But we decrease the power flow, or if we increase, now you can see that if we increase the power flow, right, the we have more dominant oscillations. We have more dominant oscillations mainly for this red curve and the blue curve here. But if we reduce the power flow, because this is minus here from the base case, then we find that the amplitude of oscillations, and then it will decay down after 7 seconds or 8 seconds, it starts decaying down. But if we have increased amount of the power flow, then we find that we have increased magnitude of oscillations, and as well as it does not damp out even after 8 seconds or 10 seconds here. Okay, so with this change which is shown here, it is from with the base case, you can say 1800 megawatt. So that's the base case is 1800. So we have reduced the power flow from 1800 megawatt, and we have increased the power flow from 1800 megawatt. So if I say this one, so the the total power flow will be 1800 plus 400, so that will be 2200 amount of the power flow. So you can see that the amplitude here, this will correspond, this is actually 22, but this is corresponds to 24, because the starting point is 1800 here, they say, right? So that is the you can say stability limit. So that could be the amount of the power flow which will correspond to the stability limit from the base case here. So maybe I will skip this part. If you have anything more.
So,
Yes.
here we are. Is this result based on that Hasle-Halden simulation, or is it for general case? Like in that case, we were increasing the load, so it moved from zero point 0.5 hertz to then 2.3 hertz as we reached the steady state stability limit.
Mm-hmm.
That the frequency decreased and the damping ratio, damping factor also reduced. So
Mm-hmm.
this is the case for that specific case, or it is a common trend that when we increase the power flow, the amplitude of oscillation increases with poor damping.
No, in general, we find in almost all the network, if we have, let's say, some amount of the loading, then we don't observe the oscillation, right? But if we increase the loading beyond a certain point, we find that the oscillations have become more, they have become more significant. We observe in most of the network, we observe that, we observe this trend, we observe this behavior in most of the network. It is not just for this example, in almost all the network we observe this. And that is why it is very important, because the loading of the line, the maximum loading that you can have on the line, it is correspond to thermal capability actually. It is not even a steady state stability limit. Maximum loading that you can have, it is not just the stability limit, it is actually correspond to the thermal capability limit. But we are never able to load the line up to the thermal capability, we are never able to, because we are constrained, we are limited by the stability limit actually. So thus the loading of the line is even lesser than stability limit. So that means if I say the stability limit, as in this case, it was 2200 megawatt, right? But thermal capability limit could be something 3000 megawatt or 3500 megawatt. So if by some means we are able to design the controller, we are able to design the controller to damp out these oscillations, right? Then in that case, we can even load the line up to 22, or what is said here, 22, 2200 megawatt as well. We can do that because that is stability limit. So it all depends upon the system parameters and how effective your controller design is actually, right? So if you have very effective controller design, then in that case you can have the power flow which will correspond to the stability limit, that is 2200 megawatt. But we have the loading of the line is, it is still lower than 2200 megawatt, because if we have the power flow which will correspond to the stability limit, right? So if we have a power flow which will correspond to the stability limit, then in that case you will have a mode of 0.3 hertz but a poor damping factor. Now it's okay. Mode oscillation is 0.3 hertz with a poor damping factor. That means if you have some disturbance, there would be some oscillations adjust. So that means the oscillation will not damp out soon. There will be an oscillation observed for certain period. It will exist for certain. But if one disturbance takes place here at 1 second, and you have a poor damping, and the oscillations have not died out, right? They have not decayed. And then following this first disturbance, if there is a second disturbance that takes place in the network, let's say and again it is a large disturbance, not a small disturbance, then it is possible that this oscillation may further increase following the second disturbance before the oscillation has decayed down. Let's say the oscillation disturbance takes place at 5 seconds and the oscillation has not decayed down. Then it is possible that these oscillations may further increase in amplitude. Then it will be difficult for the controller to damp out those oscillations. And this is the system operator. System operator may not be able to apply an effective control to damp out these oscillations. And then in that case, the generators may trip. That is possible. Right. So that is in fact, the constraint we have. So if you have effective control design, then you can have the power flow up to the stability limit. But we are very much uncertain about the disturbance that may take place in the network. If one disturbance takes place here at 1 second, another disturbance, when it is likely to take place, we do not know. All right. So if second disturbance takes place before the oscillations has decayed down, then it will be difficult for the generator to be controlled. So that is the challenge actually here. How we apply effective control to damp out these oscillations here. And that's why we keep the power flow much lower, for which we don't observe any oscillation. So that means you are not utilizing the line fully. Because maximum amount of the power flow that can flow, it is corresponding to thermal capability. But you are loading the line much lower than thermal capability, and in fact much lower than stability limit. So that is the constraint actually here. If you have the oscillations, that means you cannot load the line. So, and that is why it is very important to design the controller so that you don't observe the oscillation whenever we have a increased amount of power flow in the line. That is important here. Okay.